Hello all, have a nice time. Today we will discuss the topics coordinate representation of vectors and Gram-Schmidt orthonormalization process. In the last class we studied about orthonormal basis. So what's the use of orthonormal basis? So let V be a vector space and B is a basis of the vector space. And let B is equal to V1, V2, etc. Vn. And we have already studied that if U is any element of this vector space, then this element U can be written as a linear combination of the basis elements. That is, there exist constants C1, C2, etc. Cn such that U1 is equal to C1 V1 plus C2 V2 plus etc. plus Cn Vn. And we have already studied that the coordinate matrix representation of U with respect to this basis can be written as the column matrix C1, C2, etc. Cn using the coefficients of this combination. Actually, this result is true for any vector space V and corresponding to any basis of the vector space, you can have the coordinate representation of a vector in the vector space like this. Okay. Now, in the last class, we have studied the concept of orthonormal basis. What do you mean by an orthonormal basis? It's a basis of the vector space. Also, if you take any pair of elements of the basis, they are orthogonal and each vector have unit length. So, if B equal to V1, V2, etc. Vn is such an orthonormal basis for an inner product space V, then the coordinate representation of a vector u relative to B is u equal to inner product u v1 into v1 plus inner product u v2 into v2 plus etc. plus inner product u vn into vn. And corresponding coordinate matrix of u relative to B is this column matrix. That is, we are writing the coefficients of v1, v2, etc. vn in this expression. So the importance of the theorem is that if the basis of the vector space is orthonormal, then you can find the coefficient C1, C2, etc. Cn using this formula in a straightforward way. So here in the last module, we have calculated this coefficient C1, C2, etc. Cn by solving a system of equations. Here there is no need to solve such linear systems. Here we can find the coefficient C1, C2, etc. Cn by using the formula C1 is equal to inner product UV1, C2 equal to inner product UV2, etc. Cn equal to inner product UVn. So in a straightforward way, you can find the coordinate matrix of U relative to the basis B. So that is the importance of orthonormal basis of a vector space. Now let us have a problem. Find the coordinate matrix of U equal to 2, minus 1, 4, 3 relative to the orthonormal basis B equal to 5 by 13, 0, 12 by 13, 0, 0, 1, 0, 0, 12 by 13, 0, 5 by 13, 0, 0, 0, 0, 1. Here it is given that the basis is orthonormal. Otherwise, we have to form a system of equations and we have to find the coefficients C1, C2, C3, C4, satisfying the relation U is equal to C1 into first vector plus C2 into second vector plus C3 into third vector plus C4 into fourth vector. But since here the basis is orthonormal, you can find the C1, C2, C3, C4 using the formula given. C1 equal to inner product U V1, that is equal to U dot V1. We are considering the dot product as the inner product here. So we are taking the dot product of two vectors, 2 into 5 by 30 plus minus 1 into 0 plus 4 into 12 by 30 plus 3 into 0. Answer is 58 by 30. Similarly, C2 equal to inner product U V2, it is minus 1. C3 equal to inner product U V3, it is 44 by 30. And C4 equal to inner product U V4, that is 3. So the coordinate matrix of U relative to B is 58 by 30, minus 1, 44 by 30, 3 transpose. One more problem. Find the coordinate matrix of U equal to 5, minus 5, 2 related to the orthonormal basis B equal to 3 by 5, 4 by 5, 0, 0, 0, 1, minus 4 by 5, 3 by 5, 0. So in this problem also B is given as orthonormal. So to find the coefficients C1, C2, C3, we have to evaluate inner product UV1, inner product UV2 and inner product UV3. Inner product UV1 is 5 minus 5, 2, dot product with 3 by 5, 4 by 5, 0. Here the inner product used is dot product. So the answer is minus 1. Likewise, inner product UV2 is 2 and inner product UV3 is minus 7. So the coordinate matrix of U related to the basis B is -1, 2, -7. So we have discussed the importance of an orthonormal basis of a inner product space. Now the question is, given a basis for an inner product space, how can we construct an orthonormal basis? The process is Gram-Schmidt orthonormalization. So given a basis B equal to V1, V2, etc. Vn that may not be orthonormal, using this basis, you can construct another basis which is orthonormal also. So this is a process actually. We are providing the process without proof. In the orthonormalization process, corresponding to each vector v1, v2, etc. vn in B, we will construct the vectors w1, w2, etc. wn using this formula so that set w1, w2, etc. wn becomes orthogonal. And after producing this orthogonal set, we can construct an orthonormal basis for B. Because in orthogonal basis, you know that any pair of vectors are orthogonal. So it is enough to make the vectors as unit vectors. So we divide each vector by its norm to make it as unit length, and the set D equal to u1, u2, etc. un thus obtained becomes an orthonormal basis of V. So this is a process of Gram-Schmidt orthonormalization. So we have to study this formula, how to construct this w1, w2, etc. wn from v1, v2, etc. vn. w1 is v1 itself. And for W2, we are using V2 and W1. The formula is V2 minus inner product V2 W1 by inner product W1 W1 into W1. And W3, we are using V3 W1 and W2. Formula is V3 minus inner product V3 W1 by inner product W1 W1 into W1 minus inner product V3 W2 by inner product W2 W2 into W2, etc. So in this way, we can construct as many vectors in C as there are vectors in capital D. So this vectors W1, W2, etc. W1 is an orthogonal basis for D. And after constructing this orthogonal basis, we will divide each vector by its norm to make it as unit vector. Then the resulting vector becomes an orthonormal basis for D. So let us have some problems. First problem is find the orthonormal basis corresponding to the basis B equal to 110, 120, 012 for R3. So it is given that E is a basis for R3. And you may check whether it is orthogonal. So the dot product of first two vectors is 1 into 1 plus 1 into 2, that is 3, which is not equal to 0. So these vectors are pairwise not orthogonal. So first we will construct an orthogonal basis corresponding to this basis. So here the vectors are v1 equal to 110, v2 equal to 120, v3 equal to 012. By the Gram-Schmidt orthonormalization process, w1 equal to v1 itself, that is 110. And for W2, we are using the formula by taking the inner product as the dot product. So in R3, we are considering the inner product as the dot product. So you can use this formula V2 minus V2 dot W1 by W1 dot W1 into W1. And you can see that the answer is minus 1 by 2, 1 by 2, 0. Likewise, W3 equal to V3 minus V3 dot W1 by W1 dot W1 into W1 minus V3 dot W2 by W2 dot W2 into W2. So the answer is 002. So corresponding to each of the vectors V1, V2, V3, we have constructed the vectors W1, W2, W3. And you can check that these two are pairwise orthogonal. For example, here W1 dot W2 becomes equal to 1 into minus 1 by 2, that is minus 1 by 2, plus 1 into 1 by 2, that is 1 by 2, plus 0. So the answer is 0. Likewise, you can check whether W1 and W3 are orthogonal and also W2 and W3 are orthogonal. So this set W1, W2, W3 is an orthogonal basis for R3. Now we will construct an orthonormal basis corresponding to that set. So firstly, calculate norm of W1, norm of W2 and norm of W3. W1 is 110. So norm of W1 becomes square root of 1 square plus 1 square plus 0 square, that's equal to root 2. Similarly, norm of W2 becomes square root of minus 1 by 2 square, that is 1 by 4 plus 1 by 4 plus 0, that is root of 2 by 4, that is root of 1 by 2. Likewise, you can find norm of W3 also. So we have norm W1 equal to root 2, norm W2 equal to 1 by root 2, and norm W3 equal to 2. Now we will normalize the vectors again. U1 is equal to W1 divided by norm W1, that is 1 by root 2 into vector W1 is 110. So you have 1 by root 2, 1 by root 2, 0. And U2 is W2 by norm W2. So we have minus 1 by root 2, 1 by root 2, 0. And U3 is W3 by norm W3, that is 0, 0, 1. Now you can check whether this set U1, U2, U3 is an orthonormal basis for R3. You can see that these vectors are pairwise orthogonal, because if you take dot product of U1 dot U2, it is 1 by root 2 into minus 1 by root 2, that is minus 1 by 2, and here plus 1 by 2 plus 0. So it's equal to 0. So likewise, dot product of these two vectors and dot product of these two vectors are also zeros. So it's an orthogonal set. Also, you can check whether the norm is equal to 1. So since we have constructed U1, U2, U3 in such a way that we divided each vector by its norm, clearly its the norm of each vector must be 1. So we can conclude that this is an orthonormal basis for R3. Before going to the next problem, we have an important result again. Suppose we have the vectors v1, v2, etc. vk in some vector space V. And using Gram-Schmidt orthonormalization process, suppose you constructed the vectors u1, u2, etc. uk. Then the result is span of this set equal to span of this set. For example, suppose the vector space is R3. You have two vectors v1, v2 in R3. And by Gram-Schmidt orthonormalization process, we constructed the vectors u1, u2. The result says that span of this set, span of v1, v2 is equal to the span of u1, u2. This means that set of all linear combination of the vectors v1 and v2 equal to set of all linear combinations of the vector u1 and u2. That is, if you can express a vector in R3 using v1 and v2, then you can express it using the vectors u1 and u2 also. So we'll use it this for next problem. Find the orthonormal set corresponding to the set S equal to minus 2, 2, 1, 0, 1, minus 8, 0, 1 in R4. So here the set is not a basis of R4. We know that any basis of R4 contains 4 elements. So clearly it is not a basis of R4. These two are two vectors in R4. So what is meant by orthonormal set corresponding to the set? That means that we have to construct an orthonormal set of vectors, set of two vectors, so that span of the set equal to span of the resulting set. So you just apply the orthonormalization process and the result becomes span of the given set equal to span of the resulting set. So here v1 is equal to minus 2, 2, 1, 0 and v2 equal to 1, minus 8, 0, 1. So by formula, W1 equal to V1 itself and W2 is V2 minus V2 dot W1 by W1 dot W1 into W1. So we'll get the answer as minus 3, minus 4, 2, 1. So the result is span of the set minus 2, 2, 1, 0 and 1, minus 8, 0, 1 becomes equal to the span of the set minus 2, 2, 1, 0 and minus 3, minus 4, 2, 1. And these two vectors are orthogonal. So these vectors are actually not orthogonal. You can find the dot product. So dot product becomes minus 2 minus 16 plus 0 plus 0. It is not equal to 0 clearly. But when you take the dot product of W1 and W2, it becomes 6 minus 8 plus 2. It's equal to 0. So you can see that it is now orthogonal. And by normalizing C, we get U1 is equal to W1 by norm W1. For that, we'll consider norm W1 equal to 3 and norm W2 equal to root 30. And U1 is W1 by norm W1, that is minus 2 by 3, 2 by 3, 1 by 3, 0. And U2 is W2 by norm W2. So we'll get this answer. Now you can see that these two vectors are orthogonal, that is dot product equals 0. Also, these are unit vectors. And the result is that span of the set D becomes equal to the span of the set S. So that is what is meant by orthonormal set corresponding to a particular set. These are the problems assigned to you for today. First two problems ask to find the coordinate matrix of a vector corresponding to the given orthonormal basis. And last two problems requires Gram-Schmidt orthonormalization process to find the orthonormal basis for the subspace of given vector space spanned by the given vectors. So you just apply Gram-Schmidt orthonormalization process on the vectors v1 and v2 here.